Section 5.1, area. We can estimate the area under a curve, f of x equal 2x plus 1 by dividing the area into 4 rectangles. Depending on how we choose the rectangles, that could be an underestimate, overestimate, or something in between. If we use the left endpoints for the height of our rectangle, we'll have because this increasing function, we'll have an underestimate. So we want the area of under f of x equal to x plus 1 on the interval from 1 to 5. If we use the left endpoints of four intervals, 1, 2, 3, and 4, and f of 1, 2 times 1 plus 1 is 3, f of 2, 2 times 2 plus 1 is 5, and so forth. And the f of x is going to be the height of each of the rectangles, and the width is just going to be 1, because we divided the interval from 1 to 5 into 4 equal intervals, so each one will have length 1. So the area of each rectangle then is going to be the length times the height, or the width times the height. So it'd be 1 times f of x for each of these. Anyway, so the total area, if we use left endpoints, is going to be 24. If we use midpoints, for the first interval, it goes from 1 to 2, x goes from 1 to 2, the midpoint is 1.5. So then we compute f of 1.5. 2 times 1.5 is 3, 3 plus 1 is 4, so f of 1.5 is 4, and so forth. And again, the width of each of these rectangles is 1, and the height is going to be f of x. So the area is going to be 1 times f of x, which is f of x. Add up these 4 rectangles, and we get a total of 28. If we use the right endpoints, and again, the intervals go from 1 to 5. The first interval goes from 1 to 2, so the right endpoint is going to be, of the first interval, will be 2. So we put in f of 2, and we get 5. F of 2 is 2 times 2 plus 1, which is 5. The next right endpoint is 3, and so forth. And again, the width of each interval is 1. The height is going to be f of x. So the area will be 1 times f of x. Add these up, we get a total of 32. So the left endpoints in this particular function give us an underestimate, because you see that all the rectangles are completely enclosed in the area bounded by the function and the x-axis, and the right endpoint for this particular function give an overestimate, because you see that all the rectangles extend beyond the line f of x, and so the midpoints will give us something in between. Some of them go over and some of them go under. So anyway, so the area certainly is going to be somewhere between 24 and 32. 28 might be a good guess. That's kind of in between. But in either case, whether we use left endpoints, midpoints, or right endpoints, as we increase the number of rectangles, the area is going to get closer and closer to the actual area that is underneath the f of x. So what we want to do is take the limit as the number of rectangles goes to infinity. So n goes to infinity of r sub n. R sub n, we're going to use that to denote. Well, if we can think of it as right endpoints, or sometimes it's, or you can think of it as a Riemann sum. These are known as Riemann sums. But up here I was using L4 for the left endpoints, M4 for the midpoints, R4 for the right endpoints. But the R could also stand for Riemann sum. Riemann was one of the key figures that developed these concepts here. Anyway, the limit as R sub n goes to infinity, as n goes to infinity of R sub n, we can write this as limit as n goes to infinity of the k equal 1 to n of f of x sub k times delta x. And the Greek letter sigma means the sum. So for example, let's do an example here. The sum is, just to give an example of this notation, let's say the sum k equal 1 to n. Sometimes they use it I equal 1 to n. I think it's on the computer screen. I think a k shows up a little better than an I. So I think it's easier to read. So I like the letter k for that reason. But let's just do an example of let's say n is 4. So the summation as k goes from 1 to 4 of k squared, this is going to be 1 squared plus 2 squared plus 3 squared plus 4 squared. Well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So 16 plus 9 is 25, plus 4 is 29, plus 1 is 30. So that's just an example of a sum. We could also do, let's say the sum k equal 1 to 4 of, let's say, of just 2k plus 1. Okay, so this would be 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1 plus 2 times 4 plus 1. So this is going to be 2 times 1 is 2 plus 1 is 3. 2 times 2 is 4 plus 1 is 5. 2 times 3 is 6 plus 1 is 7. 2 times 4 is 8 plus 1 is 9. 3 plus 5 is 8 plus 7 is 15 plus 9 is 24. So it's anyway, that's sort of the idea of this sigma notation here. So in this definition here, we have the sum as k goes from 1 to n. So in this case, n is 4, but we want to eventually take the limit as n goes to infinity. Okay, so the Greek letter delta, capital delta, means change. So delta x means change in x. It represents the width of the subintervals. So this notation here, in our previous example, delta x was 1. So each subinterval had width 1. So this is change in x as x goes from 1 to 2. The change is 1. As x goes from 2 to 3, the change, or delta x, is 1. So minus 2 is 1. So delta x is the change in x. So anyway, that's the notation. And so eventually this, if we divide the, increase the number of rectangles, the area gets, of the rectangles gets closer and closer to the area of the under the curve. Okay, so there's some shortcut formulas that are going to be helpful. The summation as k goes from 1 to n of k, the shortcut formula for that is n times quantity n plus 1 over 2. Shortcut formula is summation k equal 1 to n of k squared. The shortcut formula there is n times n plus 1 times quantity 2n plus 1 all over 6. Summation k equal 1 to n of k cubed. That's n times the quantity n plus 1 over 2 and the whole thing squared. Summation k equal 1 to n of k fourth. N times the quantity n plus 1, etc. So these are some shortcut formulas that are helpful. Just to give an example of get another piece of paper here. Just an example of let's go back to our previous example. Previously we said the sum k equal 1 to 4 of k squared. We computed that to be it's 1 squared plus 2 squared plus 3 squared plus 4 squared, and that came out to be 30. But we could also use this shortcut formula here, 1 to 4 of k squared. If we use the formula here, that's going to be 4 times the quantity 4 plus 1 times the quantity 2 times 4 plus 1 all over 6. So let's try, see if we can get the same thing if we use that formula. It should give us the same answer. Summation k equal 1 to n of k squared, n times the quantity n plus 1 times the quantity 2n plus 1 over 6. So here n is going to be 4. So 4 plus 1 is 5, 4 times 5. 2 times 4 is 8, plus 1 is 9 over 6. So 4 times 5 is 20, times 9 is 180 over 6. 180 divided by 30, by 6 is 30. Okay, so that gives us the same result that we had before. So those are shortcut formulas that will be helpful. And here's a proof that for one of the first formula I had up there, a proof that the summation k equal 1 to n of k is n times the quantity n plus 1 over 2. So the summation k equal 1 n of k is going to be 1 plus 2 plus 3 plus etc. 3 dots mean etc. plus n minus 2 plus n minus 1 plus n. And then we could also write this in reverse order. This is going to be n plus n minus 1 plus n minus 2 plus etc. plus 3 plus 2 plus 1. So the order doesn't matter in addition. 1 plus 2 is the same as 2 plus 1 and so forth. So we can write this in reverse order. And if we add these, we have the sum plus the sum, that's 2 of the sum. So we have 2 times the sum, k equal 1 to n, k equals, and then add each of these. Again, the order doesn't matter in addition, so we can add these in any order. So if you add the pair the n with the 1, it's n plus 1. And then n minus 1 plus 2 is also n plus 1. N minus 2 plus 3 is n plus 1, plus etc. N minus 2 plus 3 is n plus 1. N minus 1 plus 2 is n plus 1. I'm running out of room here. And then the last one is n plus 1. So I kind of ran out of room there. But anyway, we have well, how many terms do we have here? Well, the first line sort of counts the number of terms, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to n. So we have n terms, and each of the n terms add up to n plus 1. So this means that 2 times the sum is equal to n times n plus 1. And then if we divide both sides by 2, the 2's will cancel on the left side, and we get that summation k equal 1 to n, k is equal to n times n plus 1 all over 2. There's a story about one of the famous mathematicians that helped develop calculus. He was after Newton and Leibniz. Newton and Leibniz were kind of credited with inventing calculus, but it kind of evolved over a period of, it was actually developed over a period of generations. It wasn't just those two, but Gauss came later after Newton and Leibniz, but he was one of the people that helped refine calculus, kind of develop it further. Anyway, there is a story about that, and there's not, we're not quite sure how true it is, but anyway, the story circulated that when Gauss was 4, his student his teacher was trying to keep the students busy with by giving them some work to do, and so he had them add the numbers from I think it was 1, might have been 1 to 100 or something. He wanted to add them up, and he thought that would keep them busy while the teacher was able to do some other work. And so he looked at Gauss, and Gauss was just sort of sitting there with his slate turned over, and asking what was going on, and Gauss turned over his slate, and it had the answer there. So it's so evidently, as the story goes, Gauss was able to figure out the shortcut. So if we apply this formula here to the summation k equal 1 to n of n to equal 1 to 100 of k, that's going to be n times n plus 1, so it'll be 100 times 100 plus 1 over 2. That's the shortcut formula. Well, 100 divided by 2 is 50, so it's 50 times 101, and 101 times 50, you get 0, 5, 0, 5, 5050. Anyway, that was the story that circulated. We're not quite sure if it's actually true or not. That was would have been about 300 years ago. So anyway, do an example of where we take the limit. So this is that same function we were working with before, f of x equal 2x plus 1. And we use 4 rectangles, but we said as we increase the number of rectangles, the area should get in the rectangle should get approximate the area under the curve, under the line f of x equal 2x plus 1. So let's take the limit here, and we could use left endpoints or right endpoints. It doesn't matter, but I'll use the right endpoints. Okay, so we want the limit as n goes infinity of the sum k equal 1 to n f of x I times delta x. Here this should have been xk. I'm not consistent with my notation here, but this should have been x sub k. It doesn't matter. I mean, but if I have a k here, I should have a k in the inside here. Okay, so Okay, so this is the limit as if we use right endpoints, it's going to be the limit as and it goes to infinity, summation k equal 1 to n of f of 1 plus k, and and this is on the interval 1 to 5. I didn't specify the interval. It's the same interval we had before, on the interval from 1 to 5. So the width of the interval is going to be 5 minus 1 over n. And I'll do that again, 5 minus 1 over n. Okay. So that's the interval width. So infinity, summation k equal 1 to n, f of 1 plus k times 4 over n times 4 over n. So before we had we used n equal 4 in the previous example. So then this would be just f of 1 plus k. So if k is 1, we have f of 2. So that's going to be the right endpoint, f of 2 here. We're using right endpoints. And if k is 2, we'll have 4 over 4 is going to be 1 again. And we'll have 1 plus 2 is 3. The f of 3 will be the next point. Okay, so then we can plug into the formula for f of x. Well, f of x is 2x plus 1, so it's going to be 2 times this whole expression plus 1. So this is going to be the limit as n goes to infinity, summation k equals 1 to n of 2 times 1 plus, let's say, 4k over n. I'll shorten that a little bit. 2 times 4k over n plus 1, and then the whole thing times 4 over n. Okay, so that's just this is the input for the function f of x. So f of x is 2x plus 1, so this is 2 times this whole expression plus 1, and then this is the width of the sub-interval is 4 over n. Okay, so we can distribute the 2 and combine like terms. So 2 times 1 is 2, and then add 1, you get 3. So this will be the limit n goes to infinity, summation k equal 1 to n of 3 plus, well, 2 times 4 is 8, plus 8k over n times 4 over n. Okay, and then we can also distribute the 4 over n here. Distribute the 4 over n. So this will be the limit as n goes to infinity of summation k equal 1 to n of 12 over n plus 32k over n, n squared. Okay. Okay, so we can split up this sum into 2 pieces. Limit n goes to infinity of and we could actually split up the limit in 2 pieces. Might as well do the whole thing in 2 pieces. Summation k equal 1 to n of 12 over n plus limit n goes to infinity of summation k equal 1 to n 32k over n squared. Okay, so this first sum does not have any k in it, so we can factor out the 12 over n. It'll still be within the limit. So the limit goes to infinity, 12 over n times the summation k equal 1 to n of 1. We'll factor out the 32 over n squared here. 32 over n squared summation k equal 1 to n of k. So the 32 and the n squared do not depend on k. So we can take that, factor that outside the sum. It's distributive. We're applying the distributive property. Same thing we were doing up here. We were distributing the 4 over n. Here we're kind of using the distributive property in reverse. Okay, so the summation k equal 1 to n of 1 is just 1 plus 1 plus 1 n times. So that's just going to be n. So this will be the limit. N goes to infinity. 12 over n times n plus limit as n goes to infinity, 32 over n squared. And this piece here was, we can use the shortcut formula that we just proved. That's summation k equal 1 to n of k is just going to be n times n plus 1 over 2. Okay. Get another piece of paper. Okay, so the n's will cancel here. That'll give us the limit. That's the limit as n goes to infinity of 12. Well, that's the limit of a constant. That's just that constant. So this is going to be 12 plus the limit n goes to infinity of, well, 32 divided by 2 is 16. It'll be n over n times n plus 1 over n. I'm just putting n with n here, and the number with number. 32 divided by 2 is 16. Well, n divided by n cancels. Oh, I forgot to write the limit. Oh, no, the limit's right there. This cancels. And here, if this term here, if we divide, we can distribute the denominator. So this is going to be just 1 plus 1 over n. So we'll have 12 plus the limit, n goes to infinity, of 16 times 1 plus 1 over n. And then if we take the limit now, 1 over n will go to 0. And the constants are just, the limit of constants is just a constant. So this is going to be 16 times 1 plus 0. So that's going to be 12 plus 16, which is 28. So if we take the limit, we're going to get 28. In the previous example, where we used n equal 4, well, 24. We said 24 is an underestimate. 32 is an overestimate. We use 4 rectangles. 28 was somewhere in between. The midpoints are not always going to give you the exact area. In this case, it happened to give us the exact area. When we take the limit, we get we got 28. But we can see that our overestimate was 32, our underestimate was 24. So this is consistent with what we did before. And as we increase the number of rectangles, the underestimate and the overestimate should get closer and closer together. But anyway, when we take the limit, here we got 28. Okay. Okay, so that's so we've so there in the earlier part of the course, when we were taking derivatives, we were using limits as to get the instantaneous rate of change, or the slope of the tangent line, and so in this part of the course, we're using limits to compute areas, and the two are related. We'll see how the relationship between the two a little bit later. A little bit later in the week, I guess, one of our later videos, but the two are related. Anyway, here's a third example. Example 3, a car travels at a constant rate of v of t equal 50 miles per hour from time t equals 0 hours to time t equals 6 hours. How far did the car travel? And you're probably familiar with the formula: distance equal rate times time. Distance equal rate times time. So in this case, the rate is 50 miles per hour, and the time is 6 hours. So there'd be 50 miles per hour times 6 hours would be 300 miles. So the algebraically, there's no difference between distance equal rate times time and the area of a rectangle. Area of a rectangle is equal to the length times width. Algebraically, it's just multiplication, right? It's the same operation. You're multiplying. You have two variables. You're multiplying them, and this actually shows up on a graph too. If we have if our x-axis is time in hours, and our y-axis is velocity, then the area under the velocity curve actually corresponds to the distance traveled. If you recall before, we had we were looking at velocity in terms of a slope. We had a curve, and we got the velocity, and we took a limit at and looked at it in terms of a slope. So here, the velocity is actually the curve, and the area under it now is the distance. So anyway, this is sort of so when we talk about area, actually the same principles can be applied to the distance, rate, time type problems. So we're not always just talking about area when we literally talking about area when we're talking about area under a curve. It also shows up in probability too. The area under the bell curve corresponds to probabilities. Okay, so anyway, that concludes this presentation.